Okay, so this is our textbook for Math 3580, Design and Analysis of Experiments. So this is, let's say, there's a contents of this book. Okay, so maybe our first question will be why we need a design, right? What is the purpose for design? So we say design, or purpose for design is get data. So for data, we have two kinds of data. Some data we just collect the data, right? So for data we have this. We say we just collected. We just call those data the observed data, observable data. We just collect the data is already there. We just collect the data. So the other data is we need to produce those data. We call this experimental data. Okay. So this design is just how to get those data. Okay. So how to get those data? Basic idea is how to, like, if we want to think out this main effect, we need to try to get rid of the other factors influence, right? Okay, so for example, if we wanted to compare two medicines, then we try to avoid other. The result is like we just do some experiments, we get some result. So those results may be related to drug, or maybe related to other factors, like people's age, people's gender, right? People other conditions. So in order to think out the main fact, so here main fact is medicine. So in order to think out the main factor, we need to try to avoid others. So we cannot avoid others, but we try to balance them. So this is the basic idea. Okay, so let's say, so for statistics we have one sample. We make get the data. Our main purpose is just compare which one is better. So for compare, if we so we have two samples. So those are just two sample problems or many sample problems. So we instead we have one sample t-test, one sample one sample t-test, or two sample t-test, and many sample ANOVA test. So here we say if for compare two samples, so for observable data we just compare. Let's say like compare two classes, like class 1, class 2. So we just compare. So if we want to design, if the data is like not observed, let's say we want to compare two medicines, then we should assign two medicines to different people. So here we just split people by two groups, then compare, right? Then take medicine, then compare the result. So here we have this, we call those simple comparative experiment. So how to make this comparison is more efficient. One thing is here we want is the sample size, and sample size should be equal. So if we compare two classes, we cannot guarantee class 1, class 2 have the same number of students, right? So this is observed, we cannot control. But if we can control, like if we want to compare to medicine, or compare the medicine, a medicine with placebo, then we can like split people by two groups. So we can make sure that the two groups have the same number of people, or sample size the same. Okay, so here we wanted to prove when n1 equal n2, then this way is better than if n1 not equal n2. Okay. Okay. So here we're talking about like if sample size the same, like I say, choose the sample size. Okay. So sample size the same, then we prove this way is better. Okay. Okay. So if the sample size is quite the same, so we also can put two samples as one sample. So this is called a paired comparison design. Okay, like because let's say, okay, so if two samples size same, then we can change this as one sample problem, right? So this one sample problem, this way is much better. Okay. Okay. So for chapter 3, we talking about like one single factor. What the factor means like let's compare many groups. Okay. So let's say we have like let's see, we compare many classes. Okay. Class like class 1, class 2, so here compare many classes, we use ANOVA. So here for ANOVA, like compare many classes, again we cannot guarantee the sample size are the same, right? Because those are observed data or the observable data. We just collect those data. So now let's check this. Like let's say we want to find. Let's compare. So one medicine. Like we have a medicine. So we want to determine. We want to determine each time how much medicine the patient should take. So we call it dose, right? So we want to find how much amount. So maybe we can have a 10, how about 10 or 15 or 20 or 25 like that. So we want to compare. We want to find which one, which number, which amount is better. Okay, so here we just use like many groups for those doses. We just let some people take here. Let some people take like that, right? So at the first, we say that those sample size in 1, in 2, those sample size should be the same. If we wanted to make those, if we wanted to make those design, we should do this. Okay, so samples just like a 2 sample problem. If we can control, we should make the sample sizes equal, same. Okay, and so we call those as a single fact. So here the fact is those. Okay, so this is single fact. We have just only one fact. So this fact we say has some different levels. So we should determine which level is the best one, right? So those are just experiments with a single fact. So once we have the data, so analysis those data to try to find which one is better, we use ANOVA, right? Just regular ANOVA. Okay. Okay. So for some time, we found out so ANOVA we just split this into different groups. So sometime maybe we also can do those contrast, like let's say like let's say like we have, let's say here we have 3 groups, so we can say like whether these 2 groups average is better than this one, like whether this combination for these 2 levels is better than this one. So let's say so this is just a contrast. So we can call this like if this is like let's say, so we can consider that we can compare this is whether this plus this 1 1 or 1 1, we can -1, we just compare this -2, yeah. So just we want to compare, let's say suppose this is x1 x2 x3, so we want to compare whether x1 plus x2 divided by 2, their average is better than x3. So those are contrast. Okay, so we certainly that we have some here we just discussed some examples. Okay, so those are single factor experiments. Okay, so here we, let's say, to avoid some other fact, one basic idea is landing. So what is this? The landing effects model. So even for there's a single fact, so we put a landing. What is the landing meaning here? So means like if we want to like compare those level, like 10 or 15 or 20, 25, 30, we want to determine which level is better. So we have to let some people take there's 10 level, some people take 15 level. So who take 10 level, who take 15 level? So we try to make those as randomly. Like we just pick some people randomly. So this make the other issues no much influence. Like for example, like we for patients, we have different people, right? Some male, female, or some people old, some people young. So we just try pick them randomly. So like here in this level in this 10 level we have some people young, some people old. Here also some people young, some people old, right? So the people's age can be can be balanced. If we, let's say, like, if we those group of young people or those group of older people, then the result maybe have some influence by age, right? Okay. Okay. So here, let's say, so here's one factor. If we have two factors, then we just try balanced. This balance is basically, so how balance? One way is randomize. Okay, randomize or block. So what is block? Block is, let's say we have two facts. Like here we have those this okay, those level, and we have people's age, okay, or maybe gender. So here we focus on these things. We want to determine which of those is more important. So this gender, male, female, we don't care those things effect. So we call those as a block. Okay. Okay. So let's say, so we just put those people just like that way, like okay, we have like those levels and those genders. So we just say like male, female. So we should design this way if we consider male, female, and then like here we have 10 level or 15 level or 20 level like that. So we just check for male, some male check 10 level, and females or 10 level, and this 15 levels of some male, some female, like that, right? Okay. So the results may be related to those levels and also related to the gender. But this gender effect we will not, we don't care very much. So we call those the block. So for those block, we say randomized. Okay, randomized. Okay. So there's a typical situation. Adding square is if the level quadrant just so adding square is just try balanced. Okay, so let's say adding square. What is adding square? So suppose we have like we have two factors. So that we want balanced. So let's say we have A, B, C, D, E. Suppose okay here like so we just put A, B, C like here like so a simple adding square is just like that. A, B, C, D, E, and we put A here. A, B, C, D, E, A, B, C, D, E, A, B, C, D, E, A, B, C, D, E. So such a thing is called a adding square. So what is the property for adding square? Adding square, here we have two directions, like this way or this way. Okay, right? We have two factors. So these two factors are well balanced. Like in this way, for each row we have A, B, C, D, E, A, B, C, D, E, A, B, C, D, E. Right? In each column, we also have A, B, C, D, E, A, B, C, D, E, A, B, C, D, E. So we can say, like, suppose we want to compare 5 drugs. A, B, C, D is stand for 5 drugs. So we just test each one in each position. Like for A, we put A in each condition. We test it like this A like could be like for like suppose like this is we have those conditions. Like in here we have for this factor we have 5 levels. Here those factor we have 5 levels. So we just test those A, B, C, D, E for each combination. Like for A, for this, let's say we A appear in each row, each column, right? So we just call those a Latin square. Okay, so now let's say, so here we have as one as balanced. So here incomplete. So here we say the complete block design. So okay, so here randomized complete block design. So here's the complete block design. Here's incomplete block design. So what is incomplete? Complete meanings. Complete meanings like for we can look at for like this one. Suppose like in here we test 5 of them. We test all of them. So this is complete. This is complete. We just test the 5. Okay. But so we can regard like we have 5 drugs. Let's say we have 5 something, right? 5. Let's say. We just say 5 product. Okay, for 5 something. So here. We want to compare those things, 5 product or 5 drugs, but each time we cannot compare those 5. So here we can compare those 5. Sometimes we can only compare 3. Like suppose like we need to test them, but my facility is not enough. Each time we can only test 3. So this one we can like so let's one day like day 1 we say one day I can only test 3. Day 1, so first day I can test A, B, C, right? So day 2, second one we can test this D, A, B, C, D, E, A. Suppose that. Okay, so test day 3. I can take B, C, D, and day 4 B, C, D. So E, A, B, like that. Like day 5. Okay. So like each day I can only test 3 of them. So the question is, if I just stop here, after 3 days I stop, then this is not so good because I test A twice, B twice, C twice, D twice, but E only 1 time. So this is not balanced. I need to try test each one at the same time, right? So if I stop here, Okay, so I also have some trouble. Certainly, like you can, like suppose that each day I need to test 3. So if I just test E, do not test A and B, then I waste my resources. Yeah. Or like we saying, we can consider that those like 3. Like here we also have like 3 machine or 3 something, right? So here we have those kind of problem. How many tests we need? So we also need a balanced. So those are balanced, incomplete block design. So here, day 1, day 2, day 3, day 4, different days maybe have some influence on the result. But those difference we don't care. So we call those day 1, day. Those date is a block. Okay. Okay. So those are. So let's say. So maybe we can stop here. So those are the basic idea for design. Okay. So we call those just the basic idea. Just try balance there. Okay. Okay. So we quickly can stop here and then next. Okay. Yeah, we just stop here. So you get the basic idea, right?